Imagine holding a dry strand of spaghetti between your fingers. You bend it slowly, watching the pale yellow curve form a perfect arc until, snap. But wait, look closely. It never breaks into just two pieces. Where you might expect a clean break, spaghetti shatters into 3, 4, sometimes a dozen fragments that fly in all directions. This seemingly trivial kitchen phenomenon stumped some of the greatest scientific minds for decades. Why does spaghetti never break in half? This question may sound trivial, even absurd. But in this peculiar pasta puzzle lies a profound mystery about how things break. A mystery that connects the shattering of pasta to earthquakes, fracturing glaciers, and even the behavior of subatomic particles. The humble spaghetti strand, it turns out, was hiding fundamental truths about physics that would take the world's brightest minds nearly a century to unravel. Richard Feynman, the Nobel Prize-winning physicist who helped develop the atomic bomb and quantum electrodynamics, once spent an entire evening in his kitchen breaking spaghetti strands, trying to understand this deceptively simple question. He never found the answer. That is how deep this rabbit hole goes. That is how powerful this question becomes when you truly engage with it. Why does spaghetti refuse to break in two? To understand why this problem perplexed physicists for so long, we need to travel back to the laboratories of the early 20th century, where our understanding of material science was beginning to take shape. In 1924, Alan Griffith, a British engineer working at the Royal Aircraft Establishment, was investigating why materials fail at stresses significantly lower than their theoretical breaking points. Aircraft during World War I were experiencing catastrophic failures despite calculations suggesting they should hold firm. Griffith pioneered the study of fracture mechanics, examining microscopic cracks that propagate through materials under stress. His groundbreaking paper, The Phenomena of Rupture and Flow in Solids, established the foundation of modern fracture mechanics. Griffith discovered that tiny, often invisible flaws in materials concentrate stress at their tips. Like a small tear in fabric that quickly rips when pulled, these microscopic cracks create weak points. The mathematical relationship he derived, now known as Griffith's criterion, precisely described how cracks grow when sufficient energy is available. This was revolutionary, but it didn't explain the spaghetti conundrum. According to Griffith's theory, a uniform rod under bending stress should develop a single crack at its weakest point, the area experiencing the most tension, resulting in two pieces. Spaghetti, however, didn't follow the script. Enter Ronald Johnson, an American physicist working at Bell Laboratories in the 1950s. Johnson had developed an interest in how everyday objects behave under stress after witnessing a glass cup shatter dramatically when his young daughter dropped it on their kitchen floor. The cup hadn't just broken in two. It had exploded into countless pieces, radiating outward from the point of impact. There's something fundamental we're missing about how things break, Johnson told his colleagues. The mathematics suggests one outcome, but reality shows us another. Johnson began experimenting with various materials including glass rods, wooden dowels, and, yes, spaghetti. He documented how these materials fractured under different conditions, using the high-speed photography equipment available at Bell Labs. His observations consistently showed that thin, brittle rods rarely broke into just two pieces when bent. It's as if the initial break triggers something else, he noted in his research journal. Some kind of wave that causes secondary fractures. But Johnson never published these findings. His superiors at Bell Labs encouraged him to focus on more practical research related to telecommunications. His notebooks, filled with sketches of fractured rods and mathematical calculations, were filed away and forgotten for decades. Meanwhile, across the Atlantic, Olivia Turner, a materials scientist at Cambridge University, was approaching the problem from a different angle. Turner was interested in how energy propagates through crystalline structures during fracture. Using early computer models in the 1960s, she simulated how different materials should behave when stressed to the breaking point. The computer models aligned perfectly with Griffith's theory, Turner later recalled in an interview. But when we performed the actual experiments, reality refused to cooperate. It was maddening. Turner's simulations suggested that energy should dissipate after the initial break, leaving two pieces. Yet, in her laboratory, brittle rods consistently fragmented into multiple pieces. Something was happening that neither Griffith's equations nor the early computer models could capture. The mystery deepened when Richard Feynman, one of the most brilliant physicists of the 20th century, encountered the spaghetti puzzle in the 1970s. As the story goes, Feynman was preparing dinner one night when he absent-mindedly broke some spaghetti for a pot of boiling water. He noticed the multiple fragments and became instantly fascinated. Feynman, who had helped develop the atomic bomb and made groundbreaking contributions to quantum physics, spent hours that evening breaking spaghetti and observing the results. He tried different breaking techniques, various brands of pasta, even moistening some strands to see if that would change the outcome. Nothing worked. The spaghetti always broke into 3 or more pieces. Danny Hillis, a computer scientist who worked with Feynman at Caltech, later recounted, "Feynman was stumped by spaghetti. Here was a man who had helped unravel the secrets of the atom, unable to explain why a piece of pasta wouldn't break in half. It drove him crazy. What made this problem so vexing was its simplicity. Anyone could replicate the experiment in their kitchen. The phenomenon was consistently observable and yet defied the existing mathematical models of how materials should fracture. It was a perfect example of how even the most mundane observations can reveal gaps in our scientific understanding." By the end of the 1970s, the spaghetti breaking problem had become something of an inside joke among physicists, a seemingly simple question that the greatest minds couldn't answer. Some dismissed it as a curious but inconsequential puzzle. Others suspected that hidden within this pasta problem might be insights into more complex fracture dynamics relevant to everything from earthquake science to engineering. The question remained, what mysterious forces were at work when spaghetti breaks? And more importantly, what could this tell us about how things break in the wider world? The 1980s brought new tools to physics. High-speed cameras capable of capturing thousands of frames per second, more powerful computer simulations, and advanced mathematical models for describing complex systems. These technologies would prove crucial for unraveling the spaghetti mystery. Raymond Jenkins, a physicist at MIT, became obsessed with the problem after attending a conference where Feynman's spaghetti anecdote was mentioned. Jenkins had specialized in wave propagation in solid materials and suspected that the key to understanding spaghetti fragmentation might lie in how waves travel through the pasta when it breaks. Fracture is not just about reaching a breaking point, Jenkins explained to his graduate students. It's about what happens after that initial rupture, how energy redistributes throughout the material. Jenkins and his team set up an elaborate experiment. They mounted spaghetti strands in a custom-built apparatus that could bend them at precise angles while high-speed cameras recorded the moment of fracture from multiple angles. What they captured was fascinating. The recordings showed that when spaghetti breaks, the initial fracture happens at the point of maximum curvature, exactly where you would expect it. But then something unexpected occurs. The 2 resulting pieces, suddenly released from tension on one end, straighten violently. This rapid straightening creates a wave of curvature that travels down each piece, sometimes causing secondary breaks. "It's like cracking a whip," Jenkins noted. "The energy doesn't just disappear after the initial break. It transforms and propagates." Jenkins' team published their findings in the Journal of Applied Physics in 1984, but their explanation was still incomplete. Their cameras, while advanced for the time, couldn't capture the full dynamics of the break. And their mathematical models struggled to account for all the variables involved. The plot thickened when Otto Reinhardt, an Austrian physicist, published a contradictory paper in 1986. Reinhardt argued that Jenkins' wave theory couldn't fully explain the consistent pattern of multiple breaks. Using computer simulations, Reinhardt proposed that microscopic imperfections in the spaghetti structure were the real culprits. "No strand of spaghetti is perfectly uniform," Reinhardt wrote. "These imperfections create weak points throughout the material that fail nearly simultaneously under sufficient stress." The scientific community was divided. Some researchers sided with Jenkins' wave propagation theory, while others found Reinhardt's imperfection model more convincing. Still others suggested that both mechanisms might be at play. To further complicate matters, in 1991, a team at the University of Tokyo, led by Dr. Hiroshi Nakamura, introduced yet another factor: humidity. They demonstrated that the moisture content of spaghetti significantly affected its breaking pattern. Drier spaghetti produced more fragments than slightly moistened strands. The water molecules between the starch chains act as plasticizers, Nakamura explained. They allow for more deformation before catastrophic failure. This finding introduced a new variable that previous researchers had failed to control for. Perhaps Feynman's kitchen experiments had been inconsistent because of varying humidity levels in his home? The spaghetti saga was becoming more complex, not less. By the mid-1990s, the problem had attracted researchers from diverse fields. Geophysicists noticed similarities between spaghetti fragmentation patterns and the way earthquake faults rupture. Material scientists saw parallels with how advanced ceramics fail under stress. What had begun as a quirky puzzle was revealing connections to fundamental processes throughout nature. Olivia Turner, now a senior professor at Cambridge, returned to the problem with new perspectives. Working with a team that included mathematicians and computer scientists, she developed more sophisticated simulations that attempted to integrate all the competing theories. The beauty of this problem, Turner wrote in a 1996 review paper, is that it forces us to consider how multiple physical processes interact during fracture. It's not just about a critical breaking point, but about dynamic cascades of energy. Turner's team proposed that spaghetti breaking involved at least 3 distinct physical processes working in concert. Initial stress concentration at the point of maximum curvature, elastic wave propagation following the first break, and the influence of material imperfections that create weak points. Their mathematical model, while still imperfect, could predict multiple breaks under certain conditions. Meanwhile, experimental techniques continued to improve. Rachel Jordan, a former student of Jenkins now working at Caltech, developed a new apparatus that could bend spaghetti under carefully controlled conditions while monitoring microscopic changes in the pasta structure. We needed to understand what happens at the microscopic level during breaking, Jordan explained. The starch molecules in pasta form complex networks, and how these networks fail tells us a lot about the macroscopic breaking pattern. Jordan's experiments revealed that spaghetti doesn't break in a single, clean event. Instead, microscopic failures occur throughout the pasta strand microseconds before the catastrophic break becomes visible. These microfailures weaken the strand in multiple locations, priming it for additional breaks. The years 1997 to 2000 saw an explosion of papers on the spaghetti problem, with researchers approaching it from increasingly specialized angles. Some focused on the role of torsion, twisting, in addition to bending. Others explored how the cross-sectional shape of the pasta affected its breaking pattern. Still others investigated the manufacturing process of spaghetti, questioning whether extrusion methods created internal stresses that influenced breaking. Owen Thompson, a material scientist at Stanford, proposed what he called the cascading failure hypothesis in 1999. Thompson suggested that the breaking of spaghetti was a classic example of a complex system exhibiting emergent behavior. We keep trying to reduce this problem to a single mechanism, Thompson wrote, but perhaps the answer lies in the interaction between multiple mechanisms that create a cascade of failures once the initial threshold is crossed. Thompson's hypothesis resonated with researchers studying other complex systems, from financial markets to ecosystems. The idea that simple, deterministic rules could lead to complex, seemingly unpredictable outcomes was gaining traction across scientific disciplines. As the new millennium dawned, the spaghetti breaking problem had transformed from a curious puzzle into a testbed for theories about complexity, wave dynamics, and material science. Yet, despite all the progress, a complete, universally accepted explanation remained elusive. The question had evolved from, why doesn't spaghetti break in two? To, how do we model the complex interplay of forces that lead to multiple fractures? The humble pasta strand had revealed just how challenging it can be to fully understand even seemingly simple physical phenomena. But the biggest breakthrough was yet to come, from an unexpected source. In 2001, French physicists Basile Audeley and Sebastian Nukirch became intrigued by the problem after discussing it over lunch in the cafeteria at the University of Paris. Both specialized in the mechanics of thin, flexible structures, though they had previously applied their expertise to biological systems like plant stems and insect wings. We were eating pasta appropriately enough, Audeley later recalled. Sebastian mentioned the Feynman story, and we realized that our mathematical tools might be well suited to tackle this problem. Unlike previous researchers who had approached the problem experimentally first, Audeley and Newkirch began with a rigorous mathematical analysis. They developed equations to describe the behavior of a thin, brittle rod under bending stress, with particular attention to what happens after the initial break. Their mathematical model predicted that when a thin rod like spaghetti breaks, the sudden release of bending energy sends a snapback wave, traveling along each of the resulting pieces. This wave temporarily increases the curvature as it passes through, potentially causing additional breaks if the curvature exceeds the material's breaking threshold. To test their theory, they designed precise experiments using high-speed cameras capable of capturing up to 1,000 frames per second. They carefully controlled for variables like humidity, temperature, and the diameter of the spaghetti. The results, published in Physical Review Letters in 2005, provided the most compelling explanation yet for the spaghetti puzzle. Their slow-motion videos clearly showed the snapback waves propagating through the pasta after the initial break, causing secondary breaks exactly where their mathematical model predicted. It's a beautiful example of how breaking is not just a local process. Audeley explained in interviews following the publication. The initial fracture sets off a cascade of events that can cause fractures far from the original breaking point. The Audeley-Newkirch paper sent waves through the scientific community. Here, finally, was a comprehensive explanation that integrated the observations of previous researchers into a coherent mathematical framework. Their work earned them the 2006 IG Nobel Prize in Physics, an award that celebrates research that first makes people laugh, then makes them think. Yet even this breakthrough didn't completely close the book on the spaghetti mystery. Questions remained about how the findings might apply to rods of different materials or with different cross-sectional shapes. And some researchers pointed out that while the snapback wave explained why spaghetti breaks into more than two pieces, it didn't fully account for the specific number or location of all breaks in every case. The investigation continued, with researchers applying increasingly sophisticated tools. In 2018, a team at MIT led by Ronald Heisenberg and Olivia Trent built on Audeley and Newkirch's work by investigating whether it was possible to break spaghetti into exactly two pieces, a challenge that had famously stumped Feynman. Using insights from the mathematical models developed over the previous decades, they discovered that by twisting the spaghetti strand almost 360 degrees while bending it, they could control the fracture dynamics. The twist weakened the snapback effect just enough to prevent secondary breaks. Feynman was right to be puzzled, Heisenberg said when announcing their findings. Breaking spaghetti in half is indeed very difficult under normal circumstances. But once you understand the physics, you can manipulate the conditions to achieve it. The MIT team's work, published in the Proceedings of the National Academy of Sciences, demonstrated how fundamental insights derived from the spaghetti problem could lead to practical applications in controlling how materials break, potentially valuable knowledge for engineering safer structures or designing materials with specific fracture properties. By 2020, the century-long quest to understand why spaghetti doesn't break in two had yielded a rich tapestry of insights into fracture mechanics, wave propagation, and complex systems. What began as a kitchen curiosity had driven advances in high-speed imaging, mathematical modeling, and our understanding of how materials fail under stress. The spaghetti saga exemplifies how scientific progress often works. A seemingly simple observation that defies conventional explanation leads to deeper questions, which in turn inspire new experimental techniques and theoretical frameworks. Along the way, unexpected connections emerge between the specific problem and broader natural phenomena. The turning point in understanding spaghetti fracture came with the recognition that breaking is not a static event but a dynamic process that unfolds over time. This shift in perspective, from seeing fracture as a single moment to viewing it as a sequence of interrelated events, was the key that unlocked the mystery. To truly appreciate this conceptual breakthrough, imagine yourself holding a strand of spaghetti between your fingers. As you bend it, elastic energy builds up within the pasta, much like stretching a rubber band. This energy is distributed throughout the curved strand, with the highest concentration at the point of maximum curvature. When the stress at the weakest point exceeds the material's breaking threshold, a crack forms. In an ideal world, this would be the end of the story. The spaghetti would simply separate into two pieces. But reality is far more interesting. The moment the initial break occurs, something dramatic happens. The stored elastic energy must go somewhere, cannot simply disappear. Instead, it transforms into different forms of energy. Kinetic energy that causes the two halves to move, vibrational energy that travels through the material as waves, and energy that continues to drive the propagation of the initial crack. Audely and Nukirch's breakthrough was precisely describing what happens in those critical milliseconds after the initial break. Using their equations, they showed that the sudden release of bending energy creates a snapback wave that travels along each fragment at speeds approaching 1,000 feet per second. This wave is essentially a rapid change in curvature, a violent straightening followed by a rebound in the opposite direction. As this wave propagates through the pasta, it temporarily increases the local curvature beyond what it was during the original bending. If this amplified curvature exceeds the breaking threshold of the material, additional fractures occur. It's like a whiplash effect, explained Raymond Jenkins, who had proposed a similar mechanism decades earlier but lacked the mathematical tools and high-speed imaging to fully validate it. The initial break sets off a chain reaction that ripples through the material faster than the human eye can perceive. The high-speed camera footage captured by Audely and Nukirch vividly demonstrated this process. In their videos, slowed down thousands of times, you can see the snapback wave traveling along each piece of spaghetti after the initial break. The pasta appears to wiggle violently, with additional breaks occurring precisely at the peaks of these waves. What makes this explanation so powerful is that it accounts for the consistent observation that spaghetti typically breaks into 3 to 10 pieces, rather than dozens or hundreds. The snapback waves dissipate as they travel, limiting the number of secondary breaks that can occur. Furthermore, once the pasta has broken into smaller pieces, each fragment has less stored elastic energy, reducing the likelihood of further breaks. The mathematical model developed by Audely and Nukirch also explained why the breaking pattern is somewhat predictable but not entirely deterministic. Small variations in the pasta's composition, microscopic flaws, and slight differences in how the forces applied can all influence exactly where and when the secondary breaks occur. To visualize this concept, imagine dropping a pebble into a perfectly still pond. The initial impact creates ripples that spread outward in a predictable pattern. Now imagine dropping several pebbles simultaneously at different points. The resulting wave patterns interact in complex ways, creating zones where waves amplify each other and zones where they cancel out. This is analogous to what happens within the spaghetti strand during fracture. The Audely-Nukirch model was particularly elegant because it explained the phenomenon using classical mechanics. No exotic physics or complex material properties were required. The multiple breaks in spaghetti emerge naturally from the fundamental equations describing how energy propagates through elastic materials. What's remarkable, noted Olivia Turner in a commentary on their work, is that this seemingly esoteric pasta problem ultimately hinged on principles that Newton would have recognized. The complexity arises not from the underlying physics being obscure, but from the dynamic, time-dependent nature of the process. This insight represents a broader philosophical lesson about science. Sometimes, understanding a phenomenon doesn't require discovering new forces or particles, but rather developing a more sophisticated appreciation for how familiar forces interact over time to produce unexpected outcomes. The MIT team's 2018 discovery, that twisting the spaghetti before bending it could produce a clean break into 2 pieces, provided further validation of the snapback wave theory. By adding torsional stress through twisting, they changed how energy redistributed after the initial break, dampening the snapback effect just enough to prevent secondary fractures. It's like adding a shock absorber to the system, explained Ronald Heisenberg. The twist creates internal stresses that counteract the violent straightening that normally causes additional breaks. This manipulation of fracture dynamics has potential applications far beyond the kitchen. In materials engineering, controlling how and where fractures occur is crucial for designing safer structures. From buildings that can withstand earthquakes to vehicle components that break in predictable ways during collisions to absorb impact energy. The discovery also demonstrated how theoretical understanding enables practical control. Without the mathematical framework developed over decades of studying the spaghetti problem, finding the twist and bend solution would have been nearly impossible. Perhaps most satisfying was the closure this brought to Feynman's kitchen puzzle. The great physicist, known for his insatiable curiosity and determination to understand fundamental principles, would likely have been delighted by both the elegant explanation and the practical solution. In a way, Rachel Jordan reflected, we've all been continuing Feynman's kitchen experiment for the past 50 years, each generation adding new insights and techniques until the full picture emerged. The spaghetti mystery also highlights how scientific understanding often advances. Not in a straight line from question to answer, but through a meandering path of competing theories, partial insights, technological innovations, and conceptual breakthroughs. What seemed like a simple question, why doesn't spaghetti break in two, ultimately required advances in high-speed photography, computational modeling, and the mathematics of elastic waves to answer fully. By 2020, what had once been a perplexing curiosity had transformed into a textbook example of how complex dynamics can emerge from simple physical systems. Engineering students now study the spaghetti problem as an introduction to fracture mechanics and wave propagation. Computer scientists use it to test simulation algorithms for physical systems. Materials scientists reference it when developing new theories about how composite materials fail under stress. The journey from kitchen curiosity to scientific paradigm was complete. But the implications of this understanding continue to unfold in unexpected ways. The resolution of the spaghetti breaking mystery has rippled across scientific disciplines, offering insights into phenomena far beyond the kitchen. What began as a puzzling observation about pasta has blossomed into a conceptual framework for understanding complex breaking dynamics in systems ranging from the microscopic to the geological. One of the most immediate applications emerged in materials science. Rebecca Jones, a researcher at Lawrence Berkeley National Laboratory, recognized parallels between spaghetti fracture and the breaking behavior of advanced ceramics used in everything from body armor to spacecraft heat shields. These materials typically fail catastrophically, shattering into multiple pieces rather than breaking cleanly, Jones explained. Understanding the wave dynamics that drive secondary fractures gives us a path to designing ceramics that fail more predictably, and therefore more safely. Jones and her team applied the mathematical models developed for spaghetti breaking to design ceramic composites with internal structures that dampen snapback waves. By strategically embedding softer materials within the ceramic matrix, they created pathways that absorbed and redirected fracture energy, reducing the likelihood of catastrophic shattering. The implications for protective equipment were significant. Body armor incorporating these principles could better absorb impact energy without compromising structural integrity. Vehicle components could be designed to break in controlled ways during collisions, improving safety. Meanwhile, in the field of geophysics, the spaghetti insights provided new ways of thinking about earthquake dynamics. Owen Thompson, who had proposed the cascading failure hypothesis in the late 1990s, collaborated with seismologists to apply similar concepts to fault ruptures. An earthquake isn't just a single breaking event, Thompson noted. It's a complex sequence of ruptures that propagate along fault lines, sometimes triggering additional failures at a distance. The mathematics describing spaghetti fracture gave us new tools for modeling these cascades. Thompson's team developed improved earthquake simulation models that incorporated the dynamics of stress waves traveling through the Earth's crust after an initial rupture. These models helped explain phenomena like earthquake doublets, pairs of large quakes occurring in close succession, and improved our ability to assess aftershock risks following major seismic events. The connection between pasta and plate tectonics might seem tenuous, but the underlying physics of energy propagation through brittle materials unites these apparently dissimilar phenomena. As Thompson put it, nature uses the same rulebook at different scales. In glaciology, researchers studying ice shelf disintegration found that the spaghetti breaking model helped explain the rapid collapse of Antarctic ice formations. Olivia Turner, in collaboration with glaciologists from the British Antarctic Survey, applied fracture wave dynamics to model how initial cracks in ice shelves could trigger cascading failures. When a large iceberg calves from an ice shelf, it changes the stress distribution throughout the remaining structure, Turner explained. The snapback effect can send stress waves through the ice that cause additional fractures, potentially leading to the kind of rapid disintegration we've observed in ice shelves like Larsen B. This understanding has profound implications for climate science and sea level rise predictions. By incorporating these more sophisticated breaking dynamics into ice shelf models, scientists can better predict how and when major disintegration events might occur. The spaghetti insights even found applications in biology. Ronald Jenkins, in the later years of his career, collaborated with orthopedic researchers studying bone fractures in elderly patients with osteoporosis. Osteoporotic bone doesn't just break at a single point, Jenkins observed. Often, we see multiple fractures occurring almost simultaneously. The wave dynamics that explain spaghetti breaking help us understand why one initial fracture can rapidly lead to others in weakened bone tissue. This understanding influenced treatment approaches, with orthopedic surgeons developing new techniques for stabilizing fractures that account for these cascading effects. Medical device companies began designing implants that could better absorb and redistribute stress waves following initial bone failure. Perhaps most surprisingly, the spaghetti breaking problem found relevance in the world of nanotechnology. As engineers work to develop ever smaller mechanical systems, understanding how tiny structures break becomes increasingly important. At nanometer scales, materials often behave differently than they do in bulk, but the fundamental principles of fracture wave propagation still apply. Ryan Jacobs, a nanomaterials engineer at Stanford University, applied the mathematical frameworks developed for spaghetti to model fracture in carbon nanotubes, cylindrical carbon structures just nanometers in diameter that are used in everything from electronics to composite materials. When we bend a carbon nanotube to its breaking point, we observe fracture patterns remarkably similar to what happens with spaghetti, Jacobs noted. The difference is that these fractures occur at the atomic scale and propagate at speeds approaching the speed of sound in the material. By understanding these breaking dynamics, Jacobs and his team developed methods to control fracture in nanostructures, enabling more reliable fabrication of nanoscale devices and materials with customized breaking properties. The spaghetti problem also influenced how scientists approach other complex systems where apparently simple components give rise to unexpected behaviors. The realization that multiple fractures emerge from the dynamic interplay of forces over time, rather than from some exotic new physics, reinforced the importance of studying how systems evolve rather than just their static properties. Rachel Jordan, who had continued researching fracture dynamics throughout her career, reflected on this broader impact. The spaghetti problem taught us to think differently about complexity. Sometimes, complexity doesn't require complex ingredients. It can emerge from simple components interacting in time-dependent ways. This perspective has influenced fields from economics to ecology, where researchers increasingly focus on how interactions between system components give rise to emergent behaviors that cannot be predicted by studying the components in isolation. Perhaps the most profound implication, however, has been philosophical. The spaghetti saga demonstrates how even mundane observations can open windows into fundamental aspects of reality when approached with curiosity and persistence. There's something deeply humbling about the fact that a kitchen observation stumped brilliant minds for decades, observed Owen Thompson. It reminds us that nature's complexities are never fully exhausted, that there are always deeper layers of understanding to be reached. This sentiment echoes throughout the scientific community. The spaghetti problem has become something of a parable about scientific humility, a reminder that seemingly simple questions can conceal profound insights, and that progress often requires both theoretical brilliance and dogged experimental persistence. For educators, the spaghetti breaking problem has become a powerful teaching tool. Its accessibility, requiring nothing more than dry pasta and human hands to demonstrate, combined with its rich underlying physics, makes it ideal for introducing students to concepts in materials science, wave dynamics, and complex systems. I always start my fracture mechanics course with the spaghetti demonstration, said Raymond Jenkins, who continued teaching well into his 70s. It immediately shows students that there are still mysteries in the everyday world worthy of scientific investigation. And it teaches them that understanding often comes from looking at how systems evolve dynamically, not just their equilibrium states. The century-long journey from Feynman's kitchen to comprehensive mathematical models of fracture dynamics illustrates how science progresses. Through observation, questioning, theorizing, experimenting, and refining. It's a testament to the power of scientific inquiry to illuminate the world around us, from the grandest cosmic phenomena to the most ordinary kitchen occurrences. As we continue to build on these insights, the humble strand of spaghetti, that once perplexing kitchen curiosity, stands as a reminder that profound understanding can emerge from the most unexpected places. All it takes is the willingness to ask why and the persistence to follow that question wherever it leads. As our journey through the century-long spaghetti mystery concludes, we find ourselves with more than just an explanation for a peculiar kitchen phenomenon. We've uncovered a profound truth about the nature of scientific understanding itself. The spaghetti problem reveals how seemingly simple questions can unfold into entire landscapes of discovery. What began with a broken strand of pasta led scientists through explorations of elastic wave propagation, fracture dynamics, complex systems theory, and applications ranging from earthquake prediction to nanotechnology. Each answer spawned new questions. Each insight opened doors to unexpected connections. This progression embodies what physicist Richard Feynman, the man famously stumped by breaking spaghetti, once said about scientific discovery: "The more we look at stuff, the more complicated it seems to be, and we're still only looking at the surface." Indeed, the surface of a breaking strand of spaghetti revealed depths that required generations of scientists, equipped with increasingly sophisticated tools and mathematics, to fully plumb. The explanation, when finally uncovered, was both elegantly simple in its underlying principles and richly complex in its manifestations. Perhaps most importantly, the spaghetti saga reminds us of the value of curiosity about ordinary things. In a world that often celebrates only the grandest scientific endeavors, the search for fundamental particles, the exploration of distant planets, the mapping of the human genome, the humble pasta strand demonstrates that profound insights await us in the everyday world, if only we pause to question what we observe. The next time you break spaghetti for your pot, take a moment to observe the multiple fragments. In that ordinary act, you're witnessing principles that connect the breaking of pasta to earthquakes, shattering glass, fracturing bones, and collapsing ice shelves. The same mathematics that describes those flying pasta fragments helps engineers design safer buildings. Doctors treat fractures, and climatologists predict ice shelf stability. This interconnectedness, the way fundamental principles manifest across vastly different scales and contexts, is perhaps the most beautiful aspect of the natural world that science reveals to us. The forces at work when pasta breaks in your kitchen are the same forces that shape continents and stars. Understanding one helps us understand all. As we close this exploration, consider how many other everyday mysteries might still await their explanations. What questions have you stopped asking because they seem too trivial? What phenomena have you accepted without understanding because they seem too ordinary to merit investigation? The spaghetti breaking problem teaches us that nothing is truly trivial when approached with genuine curiosity. Every phenomenon, no matter how mundane, offers a window into the fundamental workings of our universe. And sometimes, the most ordinary observations lead to the most extraordinary discoveries. In the end, the century it took to solve the spaghetti puzzle wasn't just about understanding pasta. It was about developing a deeper appreciation for how things break throughout the universe, and in doing so, building a more complete picture of how our world works. The next scientific revolution might not come from a particle accelerator or space telescope. It might begin with someone noticing something unusual in their kitchen, their garden, or their workplace, and having the curiosity to ask why, and the persistence to pursue the answer wherever it leads. The universe reveals its secrets to those who question even the breaking of a simple strand of spaghetti, reminding us that profound understanding often hides in plain sight, waiting for those curious enough to look beyond the surface of the everyday world.